The current SARS epidemic has affected everyone's life. Since 2020, the rapid spreading of the virus has caused a large number of deaths. Various closures and lockdowns around the world bring about a huge economic loss. The successive variants have made it even more difficult to fight the epidemic. After 3 years, the general public regards the epidemic as coming to an end, but is this the case? From SARS to seasonal influenza, respiratory infections have always been affecting Hong Kong. Basically, every year at a particular season, we will see relevant reports on the news. Since the infection path for the different viruses may not be the same. As a result, the effectiveness of the epidemic prevention measures may become relatively low from one case to another. Therefore, in order to prevent the occurrence of large-scale epidemics, the most effective and practical method is to quickly and effectively check the infected people.
Current method for virus detection in Hong Kong, for instance, nucleic acid detection with PCR, usually costs 200 to 300 Hong Kong dollars, and the diagnostic result can only be received the next day. Such a lengthy testing time misses the critical windows for isolation and treatment. In addition, it needs trained personnel and may not be appropriate in a point-of-care context. Rapid antigen test is convenient for testing, but its low sensitivity makes it difficult to distinguish asymptomatic infection. In the post-pandemic era, the testing of resultant antibodies is critical to the evaluation of vaccine. From our understanding in pathology, we realize the reliability of detection through a single type of biomarker is very limited. So our research group proposed a point-of-care multi-dimensional test that can detect RNA, antigen, and antibodies in our similar device. The so-called multi-dimensional detection is to probe a variety of biomarkers by using a single type of nanoprobe, so as to achieve rapid, high-precision, and high-throughput point-of-care virus detection. Our team has been investigating the application of up-conventional luminescent nanoparticle function as nanoprobe for viral detection. Numerous successful demonstration and original research have been published. Briefly, up-conventional luminescence is the conversion of incoming near-infrared light to visible light by our up-conventional luminescent nanoparticle. The color of the visible light is determined by the type of dopant inside these nanoparticles. As such, they pose low autofluorescence and exhibit a large anti-stroke shift, such that a high signal-to-noise ratio detection can be achieved. More importantly, our up-conventional luminescent nanoparticle is highly biocompatible. At the meantime, infrared light poses minimal photo damage to biological molecules. These merits pursue our nanoprobes with prestigious advantage over other conventional luminescent probes for point-of-care screening.
In light of these merits, we proposed and invented a multi-level point-of-care up-conversion luminescence testing diagnostic for viral infections. The key advantages of our device are the efficient and precise capture of the targeted biomarkers and realized simultaneous detection of multiple RNA gene sequences, the spike protein and plasma antibodies, all within one biosensor platform by coupling with excellent spectral performance rare earth-doped nanoprobes. With accurate color deconvolution and synergistic regulation of multiple rare earth dopants, a unique functional multilevel detection with high sensitivity can be achieved. Combining with the low light decay, high stability, and long lifetime of our up-conversion luminescence nanoprobe. The small footprint and high throughput of our device have a vast scope of application scenarios, including in local clinics for screening of infected individuals, hospital for investigating the effectiveness of our vicinity and the progress of recovery of patients. The device can also be applied for personal care in home and office. The simplicity of the testing procedure is shown below.
Firstly, the extracted bodily fluids from the nasopharyngeal or oropharyngeal swabs are mixed with our nanoprobes in a cuvette. The cuvette was then placed in our device and the detection commenced. The detected value was recorded and simultaneously processed in order to obtain the detection results. These values and the detection results are presented to the user's smartphone through Bluetooth. Thus, enable a fast, reliable, and accurate multi-level detection.
Through this simple demonstration, we showed the simplicity of the screening procedure through utilizing our up-conversion nanoprobes and the realization of multidimensional detection. We believe the future development of point-of-care diagnostics will be focused on achieving low-cost, simultaneous multiple biomarkers detection with high specificity and sensitivity, such that a more reliable and fast identification of infected personnel can be achieved in order to aid in the prevention of pandemic outbreaks and save lives.